Assalamu alaikum students. In previous lecture we discussed about the iron carbide diagram. In this portion previously we discussed about the microstructure of eutectide steel at the percentage weight carbon percentage weight of 0.76 percent of carbon. In this lecture, our learning objectives are to discuss about the microstructure of hypoeutectoid steel and to identify between hypo and hypereutectoid steel formation, and we'll study different processes of hypo and hypereutectoid steel formation, and also develop the microstructure of hypo and hypereutectoid steel and discuss about the different reactions that will occur during this formation. Another objective is to study the mechanical properties of these types of steel, and the main which is very important region in the iron carbide diagram is the delta region. The delta region is very important in the iron carbide diagram, so we will expand it and we will magnify the delta region and expand and will study different processes that will occur in the formation of different types of hypo and hypereutectoid steel. The slow also we will discuss the slow cooling of steel and slow cooling of hypereutectoid reactions. Hypoeutectoid alloys. The microstructure of hypoeutectoid alloys. The attached figure has been taken from the book of engineering materials written by Celester. This is the schematic representations of the microstructures of iron carbon alloy of hypoeutectoid composition. The composition containing less than 0.76 weight percent of carbon, as it is cooled from within the austenite phase region to below the eutectoid temperature. This is our main discussion interest. Our main interest is to study the reactions and to study the microstructure of the austenite region from along the y and y prime axis. So this one is the microstructure of the austenite when it is cooled down from about 850 degrees centigrade to the eutectoid temperature, below the eutectoid temperature. This is the eutectoid temperature line. The red one is the eutectoid temperature line when it is cooled down. So we will study the formation of pearlite and proeutectoid alpha and eutectoid formation step by step from point C to point F. There are four steps which will be studied: point C, point D, point E, point F. Because there are different types of formations of the microstructure occurs at each step, but we will start with the composition with the initial austenite region. So hypoeutectoid alloys, the composition to the left of hypoeutectoid of the left of the eutectoid is 0.022 to 0.76. Hypoeutectoid is a Greek letter. Hypo means less than eutectoid alloys. So it is less than eutectoid 0.76. This is 1% over here. So if we decrease it, this is almost less than 0.76%. The reaction, hypoeutectoid reaction, this is the main important reaction of the hypoeutectoid steel, in which the austenite, three types of processes occurred in this one. First, austenite will be is formed when cooled, when austenized is cooled from a given temperature, which is about 850 degrees centigrade. When it is cooled down, first alpha and austenite will be dissolved into alpha plus the ferrite plus austenite, and then after that, when it is further cooled, the reaction will be again changed from alpha to iron carbide region. So the two processes will occur. Now we will discuss the step by step. At about 875 degree centigrade, point C is this one. Point C, the microstructure will consist entirely of grains of gamma phase. These are the gamma phase regions, which is, we call it austenite region. The microstructure at this point, this is the gamma phase region is appeared from the diagram. In cooling to point D, when it is further cooled down from point C to D over here. Now if we look at the microstructure is bit changed. Some small red particles are formed at the boundaries of the austenite. So which in cooling down to point D, about 775 degrees centigrade, at this temperature 775 degrees centigrade, which is within the alpha plus gamma phase region. Now we will study step by step. When it is the cooling, we will study the cooling process and we will study the phase region. So it is crossed, or during the cooling, the Li has crossed the line MO, the line MO in the diagram. This region, when it is crossed, this region is the alpha plus gamma phase region. Both these phases will coexist is in the schematic microstructure, this one. Most of the small particles will form along the original gamma grain bodies. These are the small particles. These are formed in the original gamma phase region. The composition of the ferrite phase changes with temperature along alpha minus alpha plus gamma phase boundary. The line M, which is the line MN, the MN, over here a D, which is very near to the line MN, becoming slightly richer in carbon. As soon we cool down from point D to E, the carbon is slightly richer in during this region. So the change in the composition of the austenite is more dramatic over here from D to as we cool down the Li from D to E at point E. If we look at the point E, the alpha particles are growing dramatically at the boundaries of the austenite, the alpha ferrite particles. This will occur according to the equation alpha plus gamma minus gamma. The austenite regions become shrinking while the alpha is becoming richer in the at point E. Cooling from D to E just above the eutectoid will produce an increased fraction of the phases. The alpha particles are now grown larger over here. At this point, the compositions of alpha and gamma phases are calculated using tie line. Tie line will be constructed like here. A horizontal line here is drawn from point E, which will touch both the boundaries, and now draw perpendiculars and find out the compositions of the alpha and gamma particles. These composition, the alpha phase will contain 0.022% weight of the carbon, where the gamma phase will be the composition of the gamma phase is 0.76% weight. Just below the eutectoid point, this is the eutectoid point, just below the eutectoid line to the point F. Now the alloy is further cooled down from point E to F and have crossed the eutectoid point. All the gamma phase that was present at temperature TE at point E and having the eutectoid composition, this will be transformed to pearlite, and according to the reaction in the equation which we have discussed previously. Now in this at point at point F, all the particles are now transformed into pearlite. All the gamma particles, the gamma was shrinking in point E. Now when it is further cooled, the gamma particles are converted to pearlite and surrounded by the small region of iron carbide and alpha eutectoid. We can see some proeutectoid alpha, which is the larger portion, and the regular lamellar structure of the eutectoid and carbide. Now microstructure of the hypoeutectoid steel is further studied in this slide. The hypoeutectoid alloys contains proeutectoid ferrite. This is the proeutectoid ferrite. Now over here it is more visible. It is represented by the green region. The proeutectoid ferrite formed from formed above the eutectoid temperature, plus the eutectoid pearlite that contain eutectoid ferrite and cementite. Microstructure at point F, which we have previously highlighted, will appear as the corresponding schematic diagram in this figure over here, and the schematic diagram over here, like here. Thus the ferrite phase will be present both in the pearlite and also is the phase that formed while cooling through the phase region. The ferrite that is present in the pearlite is called eutectoid ferrite, whereas the other that formed above the TE is termed as proeutectoid, meaning pre or before eutectoid in the Greek letter. This one was formed at temperature, the boundaries were shrinking, the austenite boundaries were shrinking, and the larger proeutectoid was forming before the temperature TE. That's why we call it a proeutectoid. So the micrograph, the photomicrograph is shown over here, at which the 0.388% carbon steel. Large white regions correspond to the proeutectoid region. These large white regions are proeutectoid ferrite regions. Microstructure of hyper-eutectoid steel. For the hyper-eutectoid steel, the compositions are to the right of the eutectoid, which is between the 0.76 to 2.14. So it is to the right of the composition which we have discussed previously. Hyper-eutectoid means more than eutectoid, The eutectoid was at 0.76, while the hyper is more than 0.76 to 2.14. The reaction for the hyper-eutectoid steel, three reaction will takes three transformations will occur. One, the gamma will be transformed into gamma plus iron carbide, and then pearlite to then it will be further transformed into pearlite region plus the eutectoid iron carbide. This figure has been taken from the book of engineering materials written by Celester. This schematic representations of the microstructure of an iron carbide alloy for of hypoeutectoid composition at point C1 containing between 0.76 to 2.14 per weight percent carbon, as it is cooled within the austenite phase region to below eutectoid temperature. Our point of interest in this figure is the vertical line Z to Z prime at the composition at C, the composition at C over here. It is in the region between 0.76 to 2.14% by weight. At point G, when the alloy at composition C1 is cooled from the temperature above 900 degrees centigrade, when it is cooled down, at point G the microstructure is purely austenite gamma grains. It will not change until it crosses the boundary of PO, line PO. Once it is cooled down to and it crosses the when it is cooled down to below 800 degrees centigrade, it crosses the boundary and enters the austenite region gamma plus austenite plus iron carbide. It enters this region. At this region, the small grains of cementite are forming at the boundaries of the austenite. The cementite bond, we call it pro-cementite, means before, in Greek words before cementite. Proeutectoid cementite. Proeutectoid cementite boundaries are begin to form after the crossing the line PO. So upon cooling into the gamma plus iron carbide phase, to the point H, the cementite phase will begin to form along initial gamma grain boundaries, which is point T. This cementite is called proeutectoid cementite that will form before the eutectoid reaction. This will not change until we cross the this temperature line. As soon we cross this temperature line at point I, so this is point I, the gamma, the austenite region begin to form into the lamellar structure into pearlite and eutectoid, ferrite, and the proeutectoid austenite. So if we look at the microstructure, the larger boundaries look like proeutectoid. Why we call it proeutectoid? Because it has formed before the eutectoid temperature at point H. Now it is larger, and then the regular boundaries surrounded by the pearlite regular boundaries are formed surrounded by the eutectoid. Delta region of iron carbide diagram. Delta region is a small portion of the iron carbide diagram. This is the iron carbide diagram, while this small portion, which is this small portion is magnified over here. This small portion is the delta region of iron carbide diagram. It is very important to explain this in a separate lecture, because several reaction takes place in this delta region, and with respect to hypoeutectoid steel, it is very important. The reaction occurs below 1539 degrees centigrade at point A. It starts, the delta region starts from point A to B and to N, a small portion which is magnified over here. The horizontal line at 2720 degree Fahrenheit is this one, the horizontal line. This is the eutectic peritectic temperature line, and the peritectic reaction takes place. The peritectic reaction takes place in which this region, the region below the line AB, which is liquid plus delta iron, FCC delta iron, is converted at that peritectic temperature. The liquid plus delta iron, when cooled down, it is converted into austenite region. It is converted into austenite region. If the composition is between 0.18% to 0.5% carbon, then this liquid plus delta iron is converted into liquid plus austenite. At pure eutectic point, a peritectic point of P, which is mentioned over here, if the composition of iron is 0.18% is shown in the delta region, then a pure austenite, so the liquid plus delta is converted into austenite, followed by this reaction, the peritectic reaction. Now, if there are some points of composition of carbon starting from 0.1% carbon to 0.18% carbon, and then from 0.18% carbon to 0.50 carbon, all of these points are like the line M, P, and then the line PB. These are very important lines, separate lines, represent different types of reaction. So these are explained in the upcoming. These will be explained in the upcoming lectures. But the some over here, it is important to note about the some reactions which will take place for this region. One is the peritectic reaction at which is occurred at 2720 degrees centigrade. The other is this region also depends upon the temperature and the composition of carbon, the weight percentage of carbon. Suppose if the solution is the composition of carbon is less than 0.10%, then the liquid plus delta is converted into pure solid delta solution. Suppose if the composition is more than point M, then what will be the solution? The solution will be gamma delta plus austenite, and then when it is further cooled down to 2554, the microstructure will be different. The behavior of the microstructure below composition less than composition of 0.8, and the behavior of the microstructure which is formed by cooling down from liquid plus delta solution between the line MP to austenite region will be different from each other. So this delta region will be explained, and the reactions, three horizontal reaction. One is for the one horizontal line in the iron carbide diagram is 2720 degrees centigrade. The other is the reaction will take eutectic point, which is point E, with the followed by the horizontal line. This horizontal line will be explained further, or this this is already explained in the previous lecture. The third horizontal line, which is H, J and K, the eutectoid point at 0.8%. This is also explained in the previous lecture. So overall, this iron carbide diagram is divided into several portions, one of which is the delta region. The reaction, the most important reaction which is taking place, is the peritectic reaction. The other region is, with respect to composition, is 0 to 0.8% carbon. The steel, what is it, a hyper or hypoeutectoid steel, and then 0.2 to 0.8 to 2% weight of the carbon, and after that 2 to 4.3% weight of the carbon, and then 4.3 to 6.67. These different portion will be explained further. And then the microstructure, with respect to the microstructure, what will be the behavior of the microstructure when substance is cooled down at a composition of 2 weight percent, or if a substance is cooled down before the 2% weight of the carbon, or when the microstructure, what will be the behavior of the microstructure, how it will look like when the substance is cooled down between 0 to 0.8% carbon by weight. So these are some common questions and will be asked in the exam. One question in iron carbide diagram is to simply sketch the iron carbide diagram, and the other may be to write the reactions, different reactions taking place in the iron carbide diagram. The small portion, this is the small portion we have already discussed. We will magnify this small portion, and we will explain the different reactions which will take place in this portion. This is the expanded image of the delta region of iron carbide diagram. The horizontal line MPB represents the peritectic reaction. This is the peritectic reaction. The point M is the peritectic point at which the maximum solubility of carbon in BCC delta iron is 0.1%. If we compare this point M with the gamma solid solution, which that one is much greater, that line is much greater. The presence of carbon influences the delta to austenite region, which converts the delta to austenite region. This is the peritectic reaction. L plus delta, liquid iron solution plus delta region converts to austenite. The allotropic change occurs when the carbon is added to the iron. The temperature of the allotropic change, due to the allotropic change, the temperature is increased from 2554 to 2720 degree Fahrenheit at 0.1% carbon. The line NM represents the beginning of the crystal structure change from BCC delta iron to FCC gamma for alloys containing less than 0.1% carbon. This is the line NM, the line N to M. This one, if we draw a horizontal line,
a vertical line. This region represents the solution of carbon less than 0.1%. The line MP, the horizontal line MP, represents the beginning of the crystal structure change by means of a peritectic reaction for alloys between 0.1% to 0.8% carbon. This is the line MP, in which the carbon solution is from 0.1% to 0.18%. All those alloys are formed uh, between these percentage composition of carbon. For alloys containing less than 0.1% carbon, upon cooling, the end of crystal structure is represented by this line NP. And this line NP. When we cool, first when the solution of 0.18 or any solution between the 0.1% to 0.18% is added to the solution, then this region, the region delta plus austenite region, is for the alloys between 0.1% to 0.18% when they are cooled down. The line PB is for the alloys between 0.18% carbon and 0.50% carbon. The allotropic change begins and ends at constant temperature. At this line PB is represent the alloys between 0.18 to 0.50% carbon. What will happen if any solution carbon composition is increased from 0.5% and we cool down the region? This region is completely converted to austenite. The solution is completely converted to austenite region. So if we further classify the iron carbide diagram into two parts, one is the steel, the other is the cast iron. The steel is further divided into two sub portions according to the compositions of carbon, while the cast iron is also divided into its two portions according to the compositions of carbon. The horizontal line CED represents the eutectic reaction. CED, this line CED. This represents the eutectic reaction. Whenever the alloy crosses this line, the reaction must take place. The eutectic reaction is taken place at 2065 degree Fahrenheit. What will be that reaction? At that reaction, the eutectic point is 4.3% carbon and 2006 at 65 degree Fahrenheit. Any liquid when cross the line CE, this line CE, must solidify into mixture of two phases, austenite and cementite. If any liquid cross this temperature, 2065 degree Fahrenheit, when the metal is cooled down, when the mixture is cooled down, when the solution solidifies into austenite plus cementite. The eutectic mixture, this eutectic mixture is also called a liquidus. The reaction, this is the reaction, the liquid is transformed into austenite and cementite, but this occurs at eutectic point. If at eutectic point the substances are cooled down, the mixture is converted into austenite plus cementite. The microstructure of eutectic mixture cannot be seen because it is not stable at room temperature and another reaction takes place. What is the line GH? The line GH at line GH and at a temperature of 1666 degree Fahrenheit, the allotropic change in crystal structure of pure iron from gamma FCC to alpha FCC is converted. So this is the region of the pure crystal form of the pure iron from gamma FCC to alpha FCC. This is the ferrite region. The line H, J and K, this one, the small triangle H, J and K, what it represent? Within this region austenite and ferrite is present. This represents the eutectoid reaction. The eutectoid point is J, at which 0.8% carbon is at 33 degree Fahrenheit. At this point, at eutectoid point, the austenite is transformed into a eutectoid mixture of ferrite and cementite. This is the reaction. The reaction takes place. The mixture below the eutectoid temperature line, below point J, every alloy will consist of a mixture of ferrite and cementite. These alloy containing less than 2% carbon are known as steel. Less than 2% within this region. This is the region of the steel below 2%. Those containing more than 2% carbon are known as cast iron. This is the region of cast iron. The steel range is further divided by the eutectoid carbon content. 0.8% to 0.8% is hypoeutectoid, and between 0.8 to 2% is hypereutectoid steel. Similarly, the cast iron is also subdivided into two regions. One is hypoeutectic cast iron, the other is hyper-eutectoid cast iron. We have already studied about the basic structures of cementite, ferrite, but over here we will repeat the microstructure of cementite. We can also call it iron carbide. The chemical formula is Fe3C, contains 6.63% carbon by weight. It is a typical hard and brittle interstitial compound of low tensile strength, approximately 5000 psi, but high compressive strength, and the hardest structure that appears on the diagram. Its crystal structure is orthorhombic. Slow cooling of steel, because steel is very important with respect to mechanical properties. This is the schematic representation of the changes in microstructure during slow cooling of 0.2% carbon steel. The A portion This is in Li1 at point A. At this point, the microstructure, this is the microstructure, this is the microstructure of austenite above 1666 degree Fahrenheit. When this is further cooled from this point over here at this point, when it crosses the line GJ, the austenite is transformed by formation of ferrite grains to austenite region. Some small grains are formed at the there are some small changes occurred at the microstructure. If we further cool down, the growth of ferrite grains composition of austenite is now 0.8% of carbon, and at final position the austenite is transformed into pearlite. Well, pearlite is a mixture of ferrite and the pearlite is a mixture of previously we have studied ferrite and cementite. So we will explain the slow cooling of Li1. Li1 is a hypoeutectoid steel containing 0.2% of carbon. In the austenite range, this Li consists of uniform interstitial solid solution. The Li1, this is the range of Li1. We will study the effect of Li1 upon cooling this at a composition of 0.2% constantly. Upon slow cooling, nothing happens until the line GJ is crossed at point x1. The line is known as the upper critical line on the hypoeutectoid side and is labeled as A3. This one is labeled as A3. The allotropic change from FCC to BCC iron takes place at 1666. We have already studied the allotropic structure when the line is crossed. The line of 1666 degree Fahrenheit is crossed. Below this, the allotropic changes occur. So the x1 line at point x1, the ferrite must begin to form at the austenite grain boundaries. So since ferrite can be dissolved, very little carbon over here, if we see at point C, proeutectoid ferrite converts over here into ferrite, this one, these grains. The carbon which comes out of this solution is dissolved in the remaining austenite, so that the cooling progresses and the amount of ferrite increases. So this line is known as lower critical until if we further cool this until the critical temperature line is reached at 1333 degree Fahrenheit, the proeutectoid ferrite is starting converted into pearlite region. So as soon the point x2 is reached, we can get an equilibrium solid solution of pearlite. Slow cooling of a hyper-eutectoid steel containing 1% carbon. This is in another example of slow cooling. Previously we discussed the slow cooling of hypoeutectoid steel at 0.8%. Now what will happen if we slow cooling of Li2 occurs from above 1666 degree Fahrenheit to below 1333 degree Fahrenheit? What will be the allotropic changes and what will be the effect of the microstructure if we cool down Li2 at constantly at 1% carbon? Upon slow cooling, nothing happens until line Cj is crossed at point x3. If we cool down the temperature, nothing happens. The line ACM, this is the line ACM. This shows the maximum amount of carbon that can be dissolved in austenite as a function of temperature, because if we cool down the temperature, different allotropic changes occurred. Above the line ACM, point x3, the austenite is saturated in carbon. As the temperature is decreased, the carbon content of austenite moves down along the line ACM towards the point J. Similarly, the grains at the point x3, the grains about the boundaries of the austenite becomes is starting converting, and at point 3 austenite, some small cementite boundaries are forming at the boundaries of the at the grains level, at the grains of the austenite, and cementite network is in the transition stage, which is converting from the cementite to from austenite to cementite. As soon the point x4, if we cool down further at point x4, both the transition stage of austenite and cementite are converted into pearlite and cementite network, and this is the now equilibrium boundary conditions. So at point D, austenite transforms to pearlite at 1333 degree Fahrenheit, while the X is cementite at cementine grade. This is the microstructure of the cementite network. The photographs 1% carbon steel, so when the slow cooled at 500 times magnified.